So we are now arriving at a point in which we have seen the most basic and interesting aspects of SuperCollider as a language, and these aspects show that we can do complex things involving graphical user interfaces, involving interaction, involving sound, even if we have not directly dealt with sound generation. And in particular, in the last video, we discussed some control structures like conditionals, if, and iteration syntax. Now, starting from this, we can introduce a very important element in music making in a very general sense. Well, of course, surely we do not want to deal with the issue of defining what music is, but at the same time, it's pretty evident that music is something happening in time, and so to control time, well, that's a basic aspect of music. So how do we control time in SuperCollider? As usual, there can be many ways, and I will show you the what for me is the most relevant way, because it is at the same time easy, and it allows you to create complex time structures. Thus, in this video, I will introduce routine and task, which are sort of two twin constructs, very similar one to each other. Now we can start from iteration. So let's suppose we want to do something many times. Let's say 10 times. How do we write this? Well, we know that we can say 10 times do, and then we can add a function. This function will be evaluated 10 times. If we want to know where we are, we can define an argument with an arbitrary names. I is a very common one, and then we can do what we want. As an example, let's suppose that we want to play a note, and we know that in order to play a note, we can use this sort of black box construct like this. Now, what does this expression do? Well, actually, the point is that it's doing 10 times, generating 10 times a music event like this, playing a middle C. Okay, so this is interesting because we could think of having 1,000 notes, or maybe 10,000 notes. Well, that is something in which computation surely helps us in doing complex things. 10,000 nodes, and of course here we see 60, but maybe we can have a different value. Well, as an example, we'd like to have we could do something like this. So this is the counter going from 0 to 10,000, and here the note will be middle C, next time it will be middle C sharp, then D, and whatever. Well, of course 10,000 is a very large number. That could be tricks to make these works, but rather than thinking about these interesting aspects, that is how to deal with counter values in a meaningful way, for this moment, we will have to stick, we are sticking to a single point. So the question is, let's stick to a middle C 10,000 times. Is it creating 10,000 notes? Yes. And when these happen, that's the point. So if we are asking the interpreter to evaluate this, the interpreter will try to evaluate, to iterate over this cycle as fast as possible. So the point is that we're asking the interpreter to do one thing for 10,000 times. Fine, the interpreter will try to do this as fast as possible. Typically, what will happen is that you will gain from a, let's say, phenomenological point of view, simultaneity. So even if it's an iteration, so logically it is a sequence, and inside the computer there are many operations working sequentially, they will be performed so fast that what the result would be that you get all the notes all together, because we have not expressed any information concerning times. So we cannot make a test with 10,000 notes, but surely we can make a test with 10 notes. So if we say 10 times make a note, I think you have just heard one note, because actually all the notes are the same and are performed substantially at the same time. So the issue at stake here is not only to be able to repeat, but also to do this in a specific temporally organized way. But we are near to the solution. The solution is rather than using a normal function, the solution is to use a special function called routine. So we have a routine and we create a routine. You know that this is new, fine, so I'm skipping it. Routine, we have to pass a function to routine. So the logic is the following. Let's suppose that we assign a certain routine to a variable r, then we could do something like this. Play the routine. So let's fill this. So what can we write inside this routine? Well, actually something like this. 10 times do this. And now you may ask yourself, yes, but what's the difference between these and the first block we wrote? Well, at this moment there is no difference, but there can be difference. There can be difference because there is a special message for numbers that does not make sense outside routines, while inside routines it makes sense in a very how can I say, clear way. So something like this. Now here we are sending a message to a number. This could be also a float number, not necessarily an integer number. And if we are using this construct inside a routine, well, actually it is legal. And while calling play on routine, then the routine will execute the content of its function, so all these, and interpret any wait send to a number as stop, that is wait, and then go back. So if we execute this with play, then 10 times it will happen that we have a cycle, so perform a node C, then wait, then back here, second time, then wait, third time, and so on. So the whole cycle will require 10 seconds to be played. So let's see what happens here, if we made mistakes or not. Now 3, 4, 5, 6, 7, 8, 9, and so, well, this is interesting because we are able to create time processes. Now, as you have seen, this is interpreted as seconds. And so, of course, 1 is 1 second. Now, let's make this a little bit more interesting. So we can have something like this. And here we have a chromatic scale. Fine, we can stop. How do we stop this process? Well, actually, this is very important. You have to remember to use Control or Apple dot. This is the panic button. It blocks all sound processes and all scheduling processes. This is called a scheduling process. So if you have something going on and it doesn't stop, Control and dot is the real panic button. I think it is stop here. This can be thought as a panic button. So when I am bored of the process, I simply Control dot and I'm killing everything. That's very, very important, a lifesaver. So let's make this a little bit more complicated. Well, first of all, of course, we can have it much shorter. This will result in a sort of mess. Fine, we're still using our black box construct, but of course next videos we will replace this with something more interesting. But an interesting aspect here is that here we have these 10 times. Fine, but what about processes that never end? An infinite process. Well, you might say we are on a computer, so everything is must end because it's finite and it's discrete. And what the hell in life long for so long as infinite? Yes, but sometimes when you are making music or sound, an installation in particular, you want to work with an idea of something just going on that can be shut down from outside, but of course that it is interesting to think in terms of keep going. So, luckily, SuperCollider has a reserved word like this. That means infinite. So, let's see what happens here. Here we have an infinite cycle. This means that for infinite times, we will create a note, MIDI note 60, wait for a quarter of a second, and then go back here, and then go back here. So we will never exit this loop. So once you have infinite, you never exit the loop. That means that it's the sort of basic form for your looping process. But let's see what happens here. And I'm stopping. How do I stop this? Well, I can use this, send a message stop. And if I want to play it again, nothing happens. Why? Because routines cannot be stopped, or better, they can be stopped, but they cannot start again if first you do not reset them. So here we are first resetting and then playing. I can also use the panic button, like I have just done. Now, what can we do with this kind of organization? Well, there is something interesting. Let's suppose we want to use the counter. The point in this case is like when we had 10,000, so it becomes a little bit too big, no? So 60, 61, 83, 94, but then you easily reach something like 120, and in terms of note, it's really far too high pitch. So an interesting aspect will be to work with this counter, and a typical construct that we need an operator can be the module. So let's assume you have 12 nodes, and if you have one modulo 12, you get 1, that's fine. And if you have 11, or let's say you have 10 modulo 12, you have 10. If you have 11 modulo 12, you have 11. And what happens if you have 12 modulo 12? You get 0. So the point with modulo operator is that you have a modulo, and once you have you are over the modulo, the modulo will be used to wrap around the sequence. So this is interesting because we can use our counter going to infinite in this way. So we can have a couple of octaves. So we use 60 and we add as a base, and we add the modulo 24 of E, meaning starting from E0 up to 23, that is 60 up to 83. So let's see what happens here. I'm back. Okay, let's stop this. This is an interesting way of controlling the behavior of our system. Now, can we do something more interesting? Well, as an example, we can call something mel and have it organized. How do we organize a melody? Well, actually, typically we start from a root, and we can call as a starting point 0, and then we can think if we are used to a keyboard to intervals. So maybe we want to do something like 0, 3, and then using 0 as a pivot, 2, 7, then maybe we can have 9 and 0, 11, 2. So these are meant as intervals that we can use here, and what happened is that we want our process to go along this sequence to add a sort of starting key to this sequence. So we want to have, we have a 0, 3, 0, 2, no? Like C, E flat, C, D, but the fact that we start from C doesn't affect the shape of our melody, so it's just a base, a transposing factor like 60. So we can have a base and say that this base might be 60 on the beginning. So the point is that now we'd like to have our player going along this sequence, and each time adding the base. So we have 60, 63, 60, 62, 65, 69, 60, 71, 72. How can we do this? Well, actually, if we want, we can add a variable like pitch. It's local and it's mel. You may ask yourself, why putting mel as an environment variable? Well, actually, because in this way we can modify it in an interactive way. So var pitch should be mel E. Fine. When the counter is 0, we are here. When the counter is 1, it's here. The point is that we need a modulo. But modulo Modulo how much? Well, the modulo must be the dimension of this. How do we access the dimension of an array? Well, it's easy. If we have this, we can say mel, hey, tell me your size, please. 9. Ah, that's cool. Rather than counting by ourselves, we do something like this. So it's the counter modulo the dimension of the array. It means that it goes from 0 up to 8, and it means it will not go over the array. Otherwise, we will be trying to access to an element which is outside the array. But the point is that using its size as a modulo, we are always wrapping around the dimension, the size of the array. So here we need to place our pitch, and then here we will add our bass. So we're calculating pitch, playing pitch, and waiting for a quarter of a second. Let's see if we made some mistake. We can it's a bit strange because it's minor major. And this is getting fun, is increasing. But let's still consider this melody not that bad. So we could think of modifying this routing in order to, let's say, do something like we can call this R2. Fine. So actually, to be precise, this is R1. So we could still use our melody as a basic melody, and we could think in terms of counterpoint, minimalistic counterpoint. So the point here is we can use our melody as a basic layer, and then we could construct a second layer working in a lower octave with a larger pace. That's a sort of bass voice. And interestingly enough, we can decide to have it 1 octave lower. So in order to have it 1 octave lower, we just subtract 12 to our pitches. So rather than it being 60 as a bass, it would be 48, but that's bass minus 12. Fine. What about time? Well, we can think of having our lower voice progressing at a slowest pace. The point is that we want to have them coordinated. The easy way would be to have a sort of time octave, if you want. So we simply double the waiting time. So let's try this. Now we will have to define both our routines. So we can start our routing like this. That's the one we know. And then we have a second one. They can be stopped autonomously. Let's kill everything. Now, you might say, but what about having this working, synchronously? Well, that's not an issue because we just evaluate all at the same time. Now we have a problem here because we have to reset our routines. Now, what does it mean that we can control this process in real time? Well, actually, our base is 60. Now, let's make our base as 55, fourth lower. back to C. Because we're changing this bass that moves the reference melody, the root for all our melodies, two melodies. And of course we can go upper like 75. Maybe we like Mel, but we'd like to, let's go back to 60. This is a bit strange. We stick to minor. This is natural minor. You see, I've decided to keep this here so that if I want to go back, so that's the point. We can interact with our. It's not the. What is interesting here is not the example in itself, even if it's powerful to understand the fact that we can link programming in various ways with music generation. What is more interesting here is that we can create these programs, executing algorithms and controlling these algorithms in real time. So let's kill everything. Now, can we make this a little bit more complex? Sure, we can. A possibility, of course, would be to add a couple of other layers. But can we do this in a more clever way? So, in a more clever way, let's copy this, make a new file. Okay, so, right, of course we can. What we did here was to copy and paste a couple of voices. It's clear, but suppose we have 4 voices. Well, it would be better, surely, to have an array made up of 4 voices with a function, an array made up rather than voices of routines. So the point would be this one. Now actually we have some issues. So what am I doing here? Here, the point is that I'm creating a voices. It's an array containing processes, routines. So an array can contain everything. So a routine is just an object from a linguistic point of view. So the point is that I'm creating an array. And this array is created by filling it with a certain number of times, that is the number of my voices. Before I had 2, no? And here the point is that I need to create those voices so that they are related, so they are procedurally created. I have a counter, the counter, and well, this counter, this can be an issue because I is used here and here. So I will use C and T. Now, formatting is a bit bad here. So it's better if we do something like this. Edit, auto indent. Well, that's better. Okay, so what to do here? C and T. We're creating a routine. Fine. This is 0.5, and let's look at the base. The base should be something like minus now 12 times CNT means that when CNT is 0, here we have the base, and then we go down. Then we go down, and so we create an array of voices going lower and lower. That's something we will have for our base to keep in mind. Then let's consider what happens with times. The point is that we can have something like waiting for we still need CNT. We need CNT multiplying something. So let's consider this. So first time CNT is 0, then it will be 1, so it goes lower and pitch and slower. But the point is that the first time CNT is 0, and here it's an issue, because we will have to wait every time 0. That's a problem, because to wait like 0 is just like omitting the whole wait things, and if you have a routine performing omitting the time to wait, it will simply try to do the things as fast as possible. Substantially what happens is a big mess in terms of sound, your CPU spiking up, SuperCollider not responding. So you will do this because it's a typical mistake I am still doing. You will do this, and what happens in that case is if the interpreter is not crashing, then you will have to crash the interpreter and reboot it and start again. But you will not lose your work. That's the interesting thing in having an editor, because the work is kept into the editor. The interpreter is a different process. Fine, so we will try not to crash this. And so here we have something going a quarter of a second, then 0, a quarter of a second, half a second, 3/4 of a second. Fine, but we need to add a certain base to this, and we can add this base like could be no, what am I doing, like 0.5. okay, then let's keep our melody, which was this is the original one. Our bass will be progressively lowered, so if we start from 60 we get 48, 36, 24. It's very low, so we will start with our bass 84 in this case. As we have 4 elements, so 4 voices, 4 routines, the counter will be 0, 1, 2, 3, 4, 0, 1, 2, 3. So we will have minus 12 for 3. 12 for 3 is 36. That's fine. So let's see, probably we made some mistake. Let's see what happens here. So now we have voices, interestingly, which is an array of voices, of routines. How do we control this? Well, we can do something like this. Voices do so for every voice in for every V in voices, start, and this will be performed as fast as possible, meaning simultaneously. If we want to control everything with a unified interface, in order to stop this, we can have a second expression like this. Let's see what happens. We need 84. Fine. And let's stop it. Here we have 4 voices. Now, of course, this small process can be made more modular, like time. Now, our base time. Now, there's an interesting format between. There is an interesting relation between these two. So, if time is 0.5, then if we have this will become time, but I prefer dur because it's a duration. So dur like this, and these should be but it's half the duration, so we multiply rather than dividing. We multiplied for 0.5. So now we are respecting what we are expecting now is that we have the same result as before. Let's see. let's stop this. What is interesting in this kind of approach is that first you can do algorithmic composition in a very generic way, and it's really fun. And on the other side, these algorithmic processes are working in real time, and they can be controlled in an interactive way. Now, the point in doing algorithmic composition is, as you have seen, that you can do modular code that can be generalized. So here we have 4, but what about having 8? So rather than starting from 84, maybe we start with 96. And our duration can be very... And now we have 8 voices. It's a canon. So what is happening here is that we're using a routine, which is a very basic and easy construct to create the idea of a time-based process, meaning it's a scheduling process, and we are able to create as many of these processes as much CPU is available to us. So there is no limit. Well, yes, actually there's a technical limit, but the number of processes can be very, very high, substantially from our user perspective infinite, and it only depends if you have enough CPU to feed these processes. So as you've seen here we have started 8 processes in all all together, and we're able to control all these processes, and we can start and stop them in an interactive way. To give you an example, we can do this now. Let's add a conditional, something like well, let's do simple things. I have stopped at 2 voices, 3 voices now, because I've stopped the 0, 1, and 2. You can control and start back all this process in real time. So of course here I have used an approach, a very musical approach, because our black box is just sort of it's a synthesizer, but it works like a keyboard substantially, even if you can do complex things, because here I'm using pitch as as in equally tempered way, but we are not forced to. Let's do something. So let's suppose we have our processing. Now this is our melody. We know that we can change it. Style, because it's purely diatonic. What happens if we multiplied these pitches for half? Well, actually the point is that we will have quarter tones. And this is something like a 3/4 half step. like a small detuning. So, many interesting things can be explored just by using our, let's call it, black box synthesizer. So we had this synthesizer, it's a black box, the only things we control is a pitch expressed in MIDI notation. Well, looks like it's a really limited object, but that's the point. When you have control, like algorithmic control, even if the object is very easy, very simple, well, you can do complex things. Now, another possibility, of course, would be to make automatic harmonization. As an example, let's consider something like our routine. Oh well, we have our basic example here. So this was our first R1, and in this case, what we can do could be to create 3. Pitch plus 4, pitch plus 7. Now what happens here is that, well, it's always the same routine, no? So let's call it again R1, fine. So, and this is our original melody, bass starting from 6 in this case. Now what happened with R1 is that rather than we still going through this melody that we have defined, but for each element of the melody we calculate pitch, and then we create 3 synthesizer events played at the same time, because we wait after all those 3 have played. So just to be sure, what happened is that, yes, it's a sequence of expression, but it will be performed, executed so fast that for us it's a single time until we reach a weight. So here we have pitch, plus 4 and pitch plus 7. What is this? It's a major triad built on the basis. So we will have a sequence of major triads. Of course, it's not an harmony of that scale. It's just a sequence of major triads, but not still interesting enough. We might make it a little bit slower. And of course we can decide to have 7th chords. So, well, that's interesting. We can add 11. So now we have a major 7th chords. Can we have a sort of random harmonization? So the point is that we do not have a general harmony, but for each chord we decide something. As an example, we can decide if let's call this quality. Quality can be, and here we know something like so choose is a message you can send to an array, and it will return a random element of the array. So 3, 4 choose means choose between 3 and 4. Why? Because 3 it's the minor third, while 4 is the major third. So quality is interesting because here we had quality. Now we can make some algorithmic calculation saying if quality equals 3, well, let's do something more interesting, well, more meaningful names. If third is 3, then yes, seventh is should be assigned the value of 10. Negative case, seventh should be something like 11. What happened here? If it's a minor third, then we have a minor seventh. Otherwise, we have a major seventh. Can we write this another way? Yes, in this way. 7 shorter, easier. At this point, what happened is that here we had the fifth, which is fine, and here we have the seventh. We're still missing the fact that we need to declare seventh. Well, we can do this one shot like this. Let's see if this works. So the point is, we are scanning through this melody, whatever melody, melody, fine. Then we're choosing a third, be it major or minor. Then in relation to major or minor, the seventh is chosen, and we create a seventh chord, adding the third and the, let's say, correct 7. Let's see if this works. Now, what about if we want to debug? Well, we can ask for first, third, seventh, if we want, post line. So let's see if they are coupled. Yes, fine. Then, if we're curious about the chord, we can have something like pitch. No, we can have something like yes, let's do this. Pitch. And we get the chord in MIDI notation play. Let's try this with the minor. Now, can we complexify this a little bit? Yeah, as an example, the fact that you're in a routine doesn't prevent you to create a routine inside a routine. So it's just like your spawning processes. You spawn a process that in itself spawns another process. So as an example, we can do something like this. Yeah, I will surely do some. Well, let's avoid this. And routine. We play it directly. Let's see if I'm not making a mistake. This could be written better, but just to give you an idea. That's fine. Let's see. What is happening here? It is happening that we get arpeggios. What is an arpeggio? Well, an arpeggio typically is you have a chord, and a chord probably typically in a score, so with a certain position and time, but that certain chord must in itself spawn another project, because the chord must be played. So here we implemented this notion of arpeggio like a spawning process from a certain position. So every time we wait for half a second, but with a new chord, the new chord, we calculate the notes that we need, and we start in an inside process made up of 4 events. The first one immediately, then we always wait for a tenth of a second, and we perform the first, third, fifth, and 7 notes. Can we write this better? Surely we can, because we could write something like pitch. Well, we could do something like let's do this. 0, third, 7, 7th is do. Let's see what is. I'm getting a bit confused with all those brackets, which is indeed an issue. Now we have to close the whole routine. Fine. And we have to play this routine. Fine. Okay. And this will be arg note. Let's call this note. This should re-implement the same thing. I'm not sure. Let's see. No, there is some issue here. There is some issue at stake here. What are we doing here? We are missing something, which is exactly this, which is 60, I think. Okay, so what is happening here is that substantially we create a routine and execute it immediately. This is the definition, and this is the playing the routine, and is made up of 4 elements. We are iterating over a collection. This collection is made up of 0, third, which is or 3 or 4, 7, and 7th, which is or 10 or 11. And over these 4 numbers, we create an event by adding to n, which is 0, 3 or 4, 7, and 10, 11, by adding 60, and then we wait. So that's exactly what we did before. Of course, this is getting a little bit tricky, but it's quite short, quite complex. That's an interesting point. So the other related object, I will not spend so much time on this, is a task. Actually, you can think as a task exactly as a routine with a main difference. The difference is that you can stop a task and resume it from the position that it has reached. When you stop a routine, you have to reset, and it starts back from the beginning. A task can be stopped inside, in the middle, and start from that position. So it's pretty easy to write a task, because we can do something like this. And starts back on where it was. Well, inside the arpeggio is a bit complicated, but if you do something like this, okay, this is exactly what we did before, and we start it, and we stop. We start it, we stop it, and we resume it. There's nothing to resume. While if it is a task, we can call resume, that is start from where you are. Now this is a task. We stop and we start from where we were. So these are our two basic objects for organized time, and you see that we can have routine inside routines. So there can be a very complex situation of spawning processes. One may say, why should I use a routine rather than a task, or vice versa? Well, the point is very easy. A task, well, typically is exactly like a routine, but for some very fast switching and processing, a routine can be more precise than a task. Now, from the user perspective, I typically use a routine when I want a process that must simply be stopped and in case started from the beginning. When I'm planning to have something that can be stopped and start again in the middle, I use a task. So that's a way of thinking about things. Rather than reflecting on internal differences between tasks and routines, just think about what you have to do. We want something just starting and exhausting itself? Well, that's a routine. Do we want to have a temporal process that we can put in pause and then resume from the position that it has reached? Then you use a task. So rather than thinking technically about eventual differences, think in terms of design. So do I need a task? I use task. Do I need a routine? I use a routine. So that's the way. That's a way of thinking about these differences. In terms of interfaces, as you've seen, that's substantially the same. So the point is that there are many other ways in which you can control time in SuperCollider. Many people use a thing called event pattern. That's powerful. That's a bit more different from my point of view. It's a little bit more separated from the core linguistic organization of SuperCollider. I typically stick to routine and task because you can do whatever you want with routine and task. I just provided some ways of integrating materials in a very musical way, but of course all the things you can think about can be implemented formally, temporally by using routing or task. So I need to add an addendum to the previous video because going back I realized that there was something wrong into this process, be it a routine or a task, and so it needed to be debugged. Let's see. It's a bit to fix it. Now, converting the previous code, we mixed various things because here we have 0, but it's not 0 that we need. We need pitch, and here we need pitch plus 7. Then we have 3 and 4 and 10 or 11, 3 or 4 and 10 or 11, and they must be added to pitch. So actually this might work if we add what? If we add pitch. Maybe, by the way, it would be better to change these and to add these directly here, and plus base. That was our idea of transposition. So does this work? Well, this doesn't work because we need to add to this structure, we need to add the pitch element. So let's first try to understand what is going on. So let's debug this. Okay, now let's see the result. What is wrong here is that we are creating various minor or major 7th chords, and we're adding these to bass, fine, but we are not taking into account pitch. So we need to do something like this: n, or better, pitch plus n, which is our interval, plus base. So let's see what happens now. So this post line will give us only the form. Maybe it will be more interesting to have something like this. Like, well, we can have this posted in this way, plus base plus pitch post line. Let's see if this works or not. This is actually working, I think. Well, we'll still have to check, but it's 60, 63, 67, fine, 70, it's minor. Then we go to 3, so it's 63, minor, fifth, and another, this is the minor seventh. Okay, this is fine. So is there a lesson to be learned from this situation? Well, yes, that sometimes we have things that simply seem to work, and so we stick to the result. Okay, we are hearing something that in some sense is changing, fine. Well, no, sometimes you have to check with your ear and then understand that the result is wrong, even if you get some result and you're not getting any errors, but still the result is wrong, and you have to check it with your ears and try to understand what is going on. Again, posting data is something that might help you in understanding what is going on during the computation process.